Hello and welcome to another one of D's ADD videos. Today we're going to look at the concept of electron configurations. What is an electron configuration? Well, it's a way for us to look at the distribution of the electrons in the orbitals of the different atoms. If you remember from our earlier discussions, electrons determine the reactivity and give the unique properties to an element. So knowing the distribution of the electrons, especially in the valence shell, valence is the outermost shell, is very beneficial. So let's look at the rules for writing these electron configurations. So the first principle or rule for drawing these configurations is Aufbau. Aufbau in German means to build up, and basically you're going to start with the lowest energy shell and then build your way up. So it goes S, P, D, and then so on, F. So before I can go to P, all of S must be completely full. Before I can go on to D, all of P must be completely full, so forth and so on. Then there's Hund's rule. Hund's rule basically says whenever we have these things called the degenerate orbitals, they have to all be containing one electron prior to pairing them up. For instance, if I have 3 p orbitals, if you remember from the orbital discussion, there's one in each direction, px, py, and pz. Well, before I get to the p, Aufbau tells me that both of these must be filled, right? And then here I have to put one in each of these prior to the pairing up of these electrons. Okay, that's what Hund's rule says. Now Hund's rule comes more into play when we're dealing with orbital diagrams, like I just drew right there. And an orbital diagram is where we draw the electrons in each orbital and the distribution, in which a circle like this one here, or a line in which we can fill, like I did in my example, represents an orbital. Okay? What we will be doing when we do the configurations, we will be filling them as such. The S on the first row, then the S on the second row, and the S, or then the P on the second row, and so forth. Okay? So we should know that the atomic number, or actually I skipped a step, sorry. Each row of the periodic table gives you the coefficient for what I just wrote down. So that 1s2, 2s2, that's that principal quantum number, and it goes with the rows on the periodic table here. Okay, so for beryllium here, for instance, we would have the 1s2 and then 2s2. S is the first 2 columns here. Then we have the P, which is these last 6. Then we have the D block, the transition metals, and the F block. So color-coded in blue, S. This gold color here for P. And then we have the orangish rust copper color, D block, and then F is this purple color. All right, so with that knowledge and the fact that we must remember that for the D and for the F, there's a slight twist on that rule I just gave you. Whenever I look at a row and I'm in the D block, the transition metals that were found on this periodic table in that copper color, I have to use one less. So for instance, in this row, even though these S ones and the P ones are going to be 4, this will be a 3. Do you see it? Okay. And then by the same token, the F's down here, you're going to have to subtract 2 from the principal quantum number. All right? So keep that in mind when you're writing the electron configurations. A lot of people forget. Also, there's a couple weird scenarios that the d orbital will actually borrow some electrons, or hijack, or whatever you want to say, from the s orbital of that same valence shell. So the reason it does this is there's extreme stability if the d orbital is half full or completely full. So what happens is elements like chromium and molybdenum will borrow 1 from s. So it'll look like 4s1 and then 3d whatever, or 5s1 and 3d whatever, 5 I guess in this case. Or if we were to look on the completely full end, that would be something like platinum, palladium, silver, gold. All these guys will borrow from the D. Because if you look, here, looking at silver, it's 1 away from completely full. Gold, 1 away from completely full. Platinum, palladium, both of these could borrow 2 electrons and get completely full. All right, so you wouldn't even write the s orbital; it just would be a d on that one, on that valence shell. And I'll show you plenty of examples illustrating these rules. So make sure you check the example videos out. One last thing: if you form cations, remember cations occur from the loss of electrons. You lose them first from the s, then the p, and so forth. Okay. We want to keep that, the more complex orbitals having their electrons. So how do you actually construct an electron configuration? Well, basically what you do is you use the diagonalization method, in which you keep in mind that for the principal quantum number, i.e. the rho, in this case 1, that's how many subshells you can have. Sorry about that. So when n is 2, for instance, you can have the s and the p. All right? So forth all the way down the line. Now, I have parentheses these because there aren't enough electrons to actually use these orbitals. But for what we have, what you do is, once you get to where you're at, the order is filled as follows. You basically fill up the 1s, then the 2s, then you do the diagonals. So then it's 2p, then 3s, then it's 3p, then 4s. Then it's 3d, then 4p, then 4s. Hopefully you see the pattern now. Okay? All the way down. All right, so each orbital or subshell can have only a fixed number of electrons. All right, so for instance, the s block here can only have 2 electrons. The p block can have 6, the d can have 10, and the f is 14. Okay? So if you keep that in mind, don't forget the fact that we are subtracting 1 and 2 for the f and the d. Actually, 1 for the d and 2 for the f from the quantum number. So that's why when we're filling the 4th shell, we're going with the 3d, then the 4p. Even though the other 2 are 4, that's going to be a 3. Okay? Or for this 4f, it's on the p, 5p and 5s, but then it's going to be 6s, then 4f. So you see, even though we're on the 6th row, our f is 4. Remember, we're filling them like this. If you see a few of them being done, this will make more sense to you, but just keep in mind that n is the number of subshells. Write them out, s, p, then d, then f, and then just draw diagonals to determine the order of the filling. All right, so again, memorize the number of electrons in each. Watch the example videos. More importantly, practice, practice, practice. There will be a separate video for orbital diagrams because there are things that you must do with quantum numbers and stuff that I would like to go into that don't pertain to this discussion. So make sure you check out that video and those examples as well. Practice, practice, practice as always. Thank you and have a nice day.